Constants in Go I find to be really fascinating because in most languages constants are read-only variables. And in Go it's quite the opposite. They're not variables at all. In fact, constants really only exist at compile time. And there's some really interesting engineering decisions that were made around that. Again, Go is trying to be a very type-safe language, and there's some things that we have to be able to do with constants that probably would not have made them type-safe if they were read-only variables. But I want to also start showing you a little bit of code here, because constants not only have a parallel type system, but they come in two flavors. They can be of a type and of a kind. And that's when constants get really interesting. So let's go look at some code here, and we can start understanding the idea of kind and type. And I'm going to be showing you right here on lines 15 and 16 two constants of a kind. Notice that there's no type information here at all. It's the keyword const, a constant name, the assignment, and then these two literal values. One is an integer value, 1, 2, 3, 4, 5, and one is pi, 3.14. And the compiler can look at these numbers. You know, again, the compiler is amazing. It can do this static code analysis. And it can look at these numbers and say, oh, okay, that's an integer, and that's going to be of kind int, and 3.14, that's going to be of kind float. In fact, literal values are constants as well. They're unnamed constants, and they're constants of this idea of a kind. Now, when constants are of a kind, what that means is that they can be implicitly converted by the compiler. Yeah, and this creates some interesting side effects that we'll talk about later on. So there we are. We've got these two constants of a kind int and kind float. But if you look on lines 20 and 21, what you'll notice now is that we have constants of a type. And they're of a type because we've declared them with specific type information, int and float 64. Now, when a constant is of a type, it is bound by the laws of that type. In other words, you can't have this constant ti can't be larger than that int can be, let's say on a 32-bit environment, and that tf variable can't be a larger constant than the float 64. But if I go back to the kind constants, what makes these interesting and why I said they have a parallel type system is because the minimum precision that a constant has to have as part of the spec is 256 bits of precision. Think about that. Like, that float has a maximum of 64 bits of precision, but that kind float has that 256. Because constants have this 256 bits of precision, this kind system that we're talking about, we can consider constants to be mathematically exact. The precision levels are so high, I mean, it's hard to argue with that, okay? Like, the compiler ends up being, from my perspective, this high precision calculator. All right, so this is why I'm saying there's a parallel type system. A constant of kind float is really different than a constant of type float 64, just from a precision perspective alone. But again, these are constants, they're not read-only variables. So on line 24, what I'm showing you is that if you tried to compile line 24, well, you wouldn't be able to do that. We would get that compiler message that you see on top, because that constant can only be of uint8, and 1000 overflows that. So you see that, pretty cool. What makes constants really powerful is the idea of kind promotion. The idea that a kind can promote to either a different kind or a type in order to have like types on each side of some sort of operation. This is what makes them powerful, because without this promotion, you would have to be manually or explicitly converting things all the time. It wouldn't work. So let's take a look at some examples of that. Now, if you look on line 30, what we're doing is we're going to end up with a variable, okay, named answer. We're not going to end up in a constant, but a variable. But look at the math we're doing. We've got the value of 3, which is an integer of kind, right? The value of 3 is of kind int, multiplying a value, which again is this literal value, but this is going to be of kind float. So we really don't have the same kind on both sides of this operation. And again, normally the compiler would not implicitly do any conversions. You'd have to do this explicitly. But since this is of kind, the compiler can do the implicit conversion. And what's going to happen is the float is going to promote over int. And so now what's going to happen is 3 is going to be moved from kind int to kind float. We're going to have 2 kind floats. We can do the math, and we end up with a floating variable. That will be float 64. Remember, this is going to be of 256 bits of precision, but since it's an IEEE 754 binary decimal, we can downgrade the 256 to 64 and without the worry of, let's say, that truncation. We could never truncate integers like that, but floating point numbers we can. So we end up with that variable of float 64 based on doing math at a kind level. We have the same thing here on line 33. We've got an integer of kind, right, number 1 of kind int being divided by 3.0 of kind float. Float promotes over int, so that 1 becomes kind float, and we have technically the mathematically exact representation of 1/3. We're maintaining its constant, right? It's a constant third, so it maintains its mathematically exact representation. But if we look at the next one here, we notice that these are both of kind int. There's going to be no conversion to float, which means that this is going to be a constant of kind int. It's going to have to be 0. Now, I'm just showing you where we're doing kind promotion. But there are going to be times when you have a constant which isn't of a kind but of a type. And we're going to see that here on line 40. 1 is a constant, but it's of type int 8. And now we're going to do math. We're going to say take the literal value of 2, which is of kind int, multiply by this constant of type int 8. And now that promotion happens again. And kind always promotes to type. So the int 8 is going to rule. 2 will be explicitly converted to that int 8. We have like types. And 2 will be a constant of int 8. So I want you to remember a few things here as we're looking at this. Constants only exist at compile time. They can be of a kind. They can be of a type. If they're of a type, they follow the rules for type. That means you got to be explicit on conversions. You have to do things like that. But when a constant is of a kind, the compiler can do these implicit conversions. Remember, it's not happening at runtime. It's happening at compile time. It's safer. And we have this idea of kind promotion, where float promotes over int, and anything kind or type will promote over kind. Interesting stuff. All right, let's take a little bit more interesting things here about constants. Now, it's really hard to show you that a constant exists in a parallel type system because, again, they only exist at compile time. But I came up with a way of potentially showing you this. Take a look on line 11. On line 11, we have a constant of kind int. And this is a very large integer. It actually represents the max integer size that we can have on our 64-bit precision. But look at the constant of kind int on line 14. Look how much larger that number is. If these were really variables, you would never be able to compile this program on line 14. It would fail, right? It's the idea on line 17 that I've commented it out. Now, if I hit run, this program will compile because we have a 256-bit precision at the constant level. Watch what happens when I change that constant to be of type int64 using the same number. Suddenly it says, hey, you can't do this, it's going to overflow. So this is a way for us to see for real that constants really have a parallel type system. They have 256 bits of precision, and they're not variables at all. All right. A couple more things about constants that we're going to be working with here, and that's that iota. And iota is a really interesting idea. What it does is it allows you to create blocks of constants, like you see on line 11. We're going to use this block syntax. And what it does is it always says, in the beginning of a constant block, iota is going to always start at 0. So if you look at lines 12, 13, and 14, right, the very first line, iota is going to be 0. Then by the compiler defaults it by doing that increment to 1 and then doing an increment to 2. Now I'm being very explicit here on lines 12, 13, and 14. If we were really going to do this in code, it would be much more like line 19 through 23, where we would just set the iota initially on the first line, and then the compiler just assumes that moving forward. So we get the same effect without having to be redundant. Now, you may not want to start at 0, which means that you can do some math, right, with the idea that iota is starting at 0. So here we're saying that A3 is not going to start at 0, it's going to start at 1 by doing an initial increment, and then again from that point on, the compiler maintains that starting point throughout the list of constants. But one thing that you'll see a lot, and the time package does this, is we can use this idea to create like a bitmap of constants. So if you look at this, what we're doing is we're taking the value of 1 on line 36, and we're doing that bitwise shift to the left. And that shift to the left is going to happen automatically now on every line that follows. And I've tried to show you the bit pattern where that 1 is shifting to the left automatically for each constant in this block. So this iota idea is really powerful for setting up constants that are going to be based on some sort of integer value, whether they're going to be just values like I'm showing you 1, 2, 3, 4, or we're going to do it for like bit masking like you're seeing there between line 36 and 41. So the big takeaway here is constants are very powerful in Go. They're not variables. They're compile time only. They have a parallel type system. And remember, those literal values that you're writing, they're really constants of a kind, unnamed constants of a kind. And the compiler can implicitly convert them when there's compatibility for that. So we're going to see some of this later on in the code as well. I'm going to bring it back up. But I really do love constants, and I think it's some of the really coolest engineering that Go brings.